Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your ZyBooks Section 6.6 titled Matrix Multiplication and Graph Powers. Alright, so we saw graph powers in Section 6.5 and you may recall from that video how if I'm given a graph called G, that's a picture of some relation R, right, some set of ordered pairs. Then the graph G squared is just the composition of R with R, right? It's a picture of R composed with R, or R squared. And G cubed was, the composition of G with G with G, R with R with R. Right? Lots of composition. Right? And I did an example in the video for section 6.5 where, to find these powers of graphs, G squared, G cubed, G to the fourth, I kept doing these compositions over and over and over again. Well, what we're going to see here in section 6.6 is a much, much easier way to find what ordered pairs, what edges will be in graph powers. All right. And it's going to be through use of adjacency matrices. Now you've seen how to make an adjacency matrix for a graph before, but we're going to do now some operations with those adjacency matrices. Okay, so before we get in any graphs, I'm going to talk about what a matrix is. Now if you've taken linear algebra before, or I don't know, you've probably seen what a matrix is at this point in your mathematical career, but let's go through it anyway. Right. So an n by m matrix over a set S is an array of elements from S with n rows and m columns. Now rows go left to right, columns go up and down. And it's always, the size of a matrix is always given as the number of rows first, then a little X, a little by, a little cross, and then the number of columns second. Each element in a matrix is called an entry. The entry in row I and column J of a matrix called capital A is denoted by A with a subscript I comma J, or just sometimes IJ. A matrix is called a square matrix if the number of rows is equal to the number of columns. So there's some examples here, like this matrix has these 6 numbers in it, 1, 3, 3, negative 5, negative 2, negative 2. There are 3 rows and 2 columns, right? 3 rows of numbers going left to right, 2 columns of numbers going up and down. So this is called a 3 by 2 matrix. Now this one's particularly over the integers, right? The set Z there, because all the entries are integers, but I'm not going to really worry about stating over what set all the time. This one is a 2-row, 3-column matrix. And if you multiply the numbers of rows by columns, that'll tell you how many entries there are as well, right? 2 times 3 is 6, and you see the 6 numbers in here, right? 3 times 2 is 6. There are 6 numbers in the matrix, 6 entries. And then this last one, 2 rows, 2 columns, 2 by 2. Right? This is what they're calling a square matrix. And this is over the set 0, 1, so all these are zeros and ones. And we're going to be dealing with mostly zeros and ones in the latter part of this section. We're going to be performing Boolean algebra and Boolean computation with just ones and zeros. Okay, so very simple. Here's some matrices, some arrays of numbers with rows and columns. Which matrix is a 2 by 3 matrix? So 2 rows, 3 columns. That would be B. 2 rows, 3 columns. So matrix B. Very, very easy, right? Which matrix is a square matrix that has the same number of rows as columns? Well, let's see. 2 rows, 2 columns with the 4 entries. And what is the value of matrix A? But you notice the subscripts, it's 3 comma 2. So that means look at matrix A, look in the 3rd row, 2nd column entry. So here's matrix A, 3rd row, so I go 3rd row down, 2nd column, that's this entry right here, the number 9. So the A with the subscript 3 comma 2, or A32, I'll say, is the entry 9. Tells you the position. Okay. Now, as I've mentioned before, you have seen the terms adjacency matrix before. We have expressed graphs using matrices before. So here's a rehash of that. So a directed graph G with n vertices can be represented by an n by n matrix, a square matrix, over the set 0, 1. So all the entries of the matrix will be either 0 or 1, called the adjacency matrix for G. If matrix A is the adjacency matrix for the graph G, then the entry in the ith row, jth column will be a 1 if there's an edge from vertex I to vertex j in the graph G. Otherwise, you're going to enter a 0, right? If there's no edge between vertex I and vertex j, then the ith row, jth column entry will be a 0. So they give a very swift example here. So here's this graph on a set of 3 vertices, right? So notice the adjacency matrix has 3 rows and 3 columns. See how there's an edge from vertex 3 to vertex 1. So in the adjacency matrix, in row 3, column 1, I'm going to put the number 1, which they have highlighted in blue here. 3rd row down, 1st column to the right, there's the number 1 because there is an edge from vertex 3 to vertex 1. And the 1 right above it means there's an edge from vertex 2 to vertex 1, right? Row 2, column 1. And you can see that here, 2 to 1 has an edge. Vertex 1 has an edge to vertex 2. So in row 1, column 2, there should be a 1. And finally, there's a edge from vertex 3 to vertex 2. So in the 3rd row, 2nd column of the adjacency matrix, there'll be a 1. And you're seeing that right here where my cursor is. Everywhere else there's a 0 because there aren't edges between those vertices in those directions. Now notice that if you see, count the number of 1s there are, that's how many edges there should be in the graph. So you see here there are 4 1s, and on the graph there are 4 edges. All right. So this one, again, very simple. Here's a graph. See, it's a graph on a set of 4 vertices. So notice the matrix has a size 4 by 4. It's 4 rows, 4 columns. So they're asking here, what is the correct value for matrix, they're calling this matrix A in the position 2, 1. So that's the 2nd row, 1st column, this question mark right here where my cursor is. So the question is there an edge from vertex 2 to vertex 1? Look at the graph. No. There's not an arrow going from 2 to 1, so I should put a 0 there. And what is the correct value for matrix A in position 4, 3? That's fourth row, third column. That's this other question mark in the fourth row here, third column. So again, if it's a 0 if there is an edge from 4 to 3. It's a 1. I'm sorry, if there isn't an edge, and it's a 1 if there is an edge from 4 to 3. Well, look at the graph. There is an edge from vertex 4 to vertex 3. So there's in row 4, column 3, there'll be a 1. So it should be very easy to make these adjacency matrices with zeros and ones when you're looking at a graph. And the other way around too, if you're given a matrix, you should be able to easily draw a graph that corresponds to that adjacency matrix. All right. So if mathematical operations, such as addition and multiplication, are defined on a set S, then matrix addition and multiplication can be defined for matrices over the set S. So what we're seeing with these adjacency matrices are Boolean matrices. Right? A Boolean matrix is a matrix whose entries are from the set 0, 1. So all zeros and ones. And we have seen Boolean addition and Boolean multiplication, right, back in chapter 5. So they're used in adding and multiplying entries of a Boolean matrix. So this material presents matrix addition and matrix multiplication for square Boolean matrices. Because those operations can be used to compute the transitive closure of a graph, right? This might sound familiar. Remember, the transitive closure of a graph came up in section 6.5. All right, the transitive closure of a graph, if you recall, was the smallest relation, the graph with the smallest number of edges that was both transitive and contained all the edges from the original graph. Matrix multiplication and addition can also be defined for general rectangular matrices, right, over other sets such as integers and the real numbers. Okay. Right. The product of two matrices A and B is well defined only if I'll highlight this, the number of columns in A is equal to the number of rows in B. All right. You cannot multiply matrices A and B in the order A times B unless the number of columns of the left matrix is the same as the number of rows of the right matrix. All right, so let me show you an example. All right. So this is matrix multiplication. So again, to multiply matrices, say A times matrix B. The number of columns of the left matrix must be equal to the number of rows of the right matrix. All right, so for example, if I took A times B and this matrix was, say, a 2 by 3 matrix, 2 rows, 3 columns, then this matrix would have to have 3 rows. Right? The number of columns of the left matrix must be equal to the number of rows of the right matrix. And say this is a 3 by 5 or something, 3 rows, 5 columns. Now the product, all right, the product, say matrix C, the size of the product will be then determined by these outer numbers. Okay, this first number, so the number of rows of the left matrix will be the number of rows of the product. and the number of columns of the right matrix will be the number of columns of the product. All right, so if I have a 2 by 3 matrix and I multiply it by a 3 by 5 matrix, the resulting matrix, say capital C, will be a 2 by 5 matrix. It'll have 2 rows and 5 columns. So in general, if I have 2 matrices and I'm multiplying them, if the left matrix is, say, an M by N matrix, right, well, then the right matrix has to have N rows. Right? There are N columns in the left matrix. This right matrix will have to have N rows. And say it's an N by, P matrix. And then the resulting matrix, the product C, will have M rows, P columns, these two outer numbers. It'll be an M by P matrix. Right? Now, if the two inner numbers aren't the same, again, if the number of columns of the left matrix is not the same as the number of rows of the right matrix, then you cannot multiply. Multiplication is not well defined in that case. All right, so that's at least addressing the size issues. Now, the nice thing about what we're going to be doing is that all our matrices will be square, and we're going to be multiplying square matrices of the same size. So a 2 by 2 times a 2 by 2, and that'll give us another 2 by 2. So the nice thing about what we're going to be doing in this section is all our matrices should be of the same square size. All right, now how is this done? All right, how is this done? So each entry of the matrix A times B is computed by taking what's called the dot product of a row of A and a column of B. And then they define the dot product in the next sentence. So if A and B are n by n square matrices, the dot product of row I of A and column J of B is the sum of the product of each entry in row I from A with the corresponding entry in column J from B. So let me show you an example. All right, and we're going to be doing Boolean addition and Boolean multiplication. So I'll pull up these matrices here. I'll write them on a piece of paper and show you what the resulting product A times B, and I'll do the other way around. I'll do B times A, because you're going to notice that when you multiply two matrices, the order matters. A times B is not necessarily going to be equal to B times A when multiplying matrices. All right. So for example, I've written down the two matrices from the activity. All right, they're both 3 by 3 matrices, right? 3 rows, 3 columns. So when I multiply them, I can actually multiply them, right? A 3 by 3 times a 3 by 3 will be another 3 by 3. So let's say A times B is equal to C. All right, and this is going to be another 3 by 3 matrix. So it's going to have 9 entries. I remember what I'm going to call them, C11, C12, right, first row, second column, C13, and then the second row, you have C21, C22, C23, third row, C31, third row, first column, C32, and finally C33, right? So it's going to have 9 entries. Now, when multiplying matrices, how do I find these entries? Okay, to find the product, C11. To find this entry here, right? So I'll focus on C11 right now. You take the dot product, right? That dot product they mentioned of the first row of A, right? So you're going to use the first row of the left matrix, which is A in this case, and first row of the left matrix, and then do the dot product with the first column of B, or the right matrix, right? The matrix on the right of this product. So the dot product of, row 1 of A with column 1 of B. And then what is that calculation? All right, so row 1 of A is this row here. There's row 1 with the entries, left to right, 1, then 1, then 1. Column 1 of matrix B is this column here. And you go top to bottom. All right, you go left to right when you're talking about the entries of a row. You go top to bottom when you talk about the entries of a column. So the entries in order are 1, 0, 1. This dot product of a row from A with a column from B is you take the product of each corresponding entry and then add them up. So I take the first entry of A, row 1 of A, with the first entry of column 1 from B. We multiply those. So 1 times 1. And then we add to this the product of the second entries, 1 and 0. And then I add to this the product of the third entries, 1 and 1. Now, do not forget, this is Boolean arithmetic we're doing. 1 times 1 was 1. 1 times 0 was 0. 1 times 1 was 1. 1 plus 0 was 1. And 1 plus 1 was 1. Remember, it was Boolean arithmetic, just ones and zeros. So for their product, first row, first column entry is 1. Right? And I do the same stuff for the other entries, right? When I want the first row, second column entry, C12, I take this dot product of the first row of the left matrix, so the first row of A, and the second column, right? First row, second column. I take the first row of the left matrix A, do the dot product with the second column of the right matrix B, right? With the second column of B. All right, so I already have the first row of A highlighted. Now I'm looking at the second column, which is the 0, 0, 1. So first I multiply the first entries, 1 times 0, plus multiply the second entries, 1 times 0 again, plus multiply the third entries, 1 times 1, and we're doing Boolean. This is 0 plus 0, which is 0, plus 1 is 1. So first row, second column, entry of the product is 1. Okay, and let's do first row, third column entry. So C1 comma 3 here, C13. What's the first row, third column entry? So now I'm looking at the first row of the left matrix, A, 1, 1, 1. And now I'm looking at the third column of the right matrix. So now I'm looking at 1, 1, 1 again. So we get 1 times 1 plus 1 times 1 plus 1 times 1. I mean, this is just 1, right? When we're doing Boolean arithmetic. All right, so the first row of the product is all 1s. Okay. Now, let's take a look at the second row entries. What's C, 2 comma 1. So if I want the second row first column entry of the product, means I'm taking the second row of the left matrix, which is A. So now I'm using the second row of A, which is 1, 0, 1 in that order, with the first column of B. So I'm back here on the first column with the 1, 0, 1. So 1, 0, 1 with 1, 0, 1, doing the dot product. So that's 1 times 1 plus 0 times 0, right? The product of the second entries plus 1 times 1, the third entries. 1 plus 0 is 1 plus 1 is 1. So 1 again. All right. Then for the second row third column, or sorry, second row second column, take the second row of the left matrix, 1, 0, 1, do the dot product with the second column of the right matrix, 0, 0, 1. Now 1 times 0 is 0, 0 times 0 is 0, 1 times 1 is 1, 0 plus 1, 0 plus 0 plus 1 is 1 again. Right. Basically, if you ever get a 1 times a 1, you're going to have 1 in the end. All right. So look at this, first, second, the first entry is a 1 for the second row here. The first entry is you're going to have 1 for this one as well. When you do the second row with the third column dot product, it'll be 1 plus 0 plus 1. And finally, looking at the third row, right, and then the third row of the left matrix with the first column, then the second column, then the third column of the right matrix, doing the dot products. So third row first column will be 0 times 1 plus 1 times 0 plus 0 times 1. Hey, none of those are 1. Each one of those has a 0 in it, so finally you get a 0. Then third row with the second column dot product, 0 plus 0 plus 0 again. And finally, the third row with the third column, 0 plus, there's a 1. All right, if you ever have a 1 times 1 in these dot products, it's going to add up to 1. Boolean. So here's the product of A and B when you do A times B. Now, let me do B times A. All right, let me show you B times A. So B times A is this. Now the matrix on the left is matrix B. So I'm going to write B here is 1, 0, 1, 0, 0, 1, 1, 1, 1. There's matrix B times matrix A had the 1, 1, 1, 1, 0, 1, and 0, 1, 0. And it's a 3 by 3 multiplied by a 3 by 3. So the result will be a 3 by 3. So I have 9 entries to fill. So now the first row, first column entry of this product, now I'm taking the first row of B, right, the first row of the left matrix, dot product with the first column of the right matrix. So you have 1 times 1, so this is going to be 1. There's a 1 times 1 there. 1 times 1 plus 0 times 1 plus 1 times 0. 1 plus 0 plus 0 is 1 when you're doing in Boolean. And then I'm doing first row, second column, right? First row, second column. So 1 times, there's a 1. If there's ever a 1 times 1, the sum is going to be 1. And then first row, third column, 1 times 1, 1. Now, I'm filling in the second row of the product. Let's take the second row of the left with the first column and second column and third column of the right. So I have 0, 0, 0. Ah, 0. Look, now can you see? Can you see how these are not the same? A times B here is not the same matrix as B times A. All right, then second row, second column, you got 0, 0, and 1, so 1. Second row, third column, you'd have 0, 0, 0, so 0. That second row is not the same as the second row when I did A times B. And then finally, I'm doing the third column of the left with the, third row of the left with the columns of the right, doing the dot products. So I got 1 times 1. All right. If there's ever a 1 times 1, the sum will be 1. So there's all 1s here. There's 1s in there, 1s in there. So it's going to be 1, 1. All right, it'll be 1 times 1 plus 1 times 0 plus 1 times 1. And then 1 times 1 plus 1 times 1 plus 1 times 0. There's a 1 times, again, if there's a 1 times 1 anywhere in that sum, you're going to have a sum of 1 in Boolean. But again, notice these are not the same matrix. So you see that, generally A times B is not necessarily going to be equal to B times A. So order matters. Okay, again, order matters when you're multiplying matrices. Now, we're going to go even nicer than that. And instead of multiplying two different matrices, we're going to be multiplying the same matrix by itself over and over and over again, so the order won't matter. But in general, the order will matter. Okay. All right, so that's matrix multiplication. And again, we're doing Boolean arithmetic here. All right, so they go through the example here. Okay, cool. So here, if this is matrix A and this is matrix B, what is the dot product of row 3 of matrix A and column 2 of matrix 3? So row 3 of matrix A is 0, 1, 1. Column 2 of matrix B is 1, 1, 1. There's definitely a 1 times 1 in there, so 1. Again, don't be confused and put 2. We're doing Boolean, so it's going to be 0 or 1, your final result. All right, and I'll let you do that one. All right, so as I mentioned, if A and B are n by n matrices over the integers, then the matrix product of A and B, denote A times B or A dot B there, is another n by n matrix such that A, B, I, J is a result of taking the dot product of row I of matrix A and column J of matrix B. I just went over all this. All right, so here's another example. You can read through how they got matrix C here. All right, and then you're just asked to fill in the blanks for these. I'll leave these to you. Okay, just fill in the question marks with, if you multiplied, notice it's A on the left, B on the right, so they're doing A times B. All right, so now we get into the powers of matrices. Multiplying a matrix, by itself over and over again. So matrix multiplication is associative, right? Meaning that if A, B, and C are all square matrices, then A times the quantity BC is equivalent to the quantity AB times C, right? So notice the order didn't change, right? Because again, order matters. It's just which two you multiplied first changed, but you still get the same result, right? Matrix multiplication is associative, but it's not commutative, right? I've already shown you that, right? A times B is not necessarily equal to B times A. So just keep that in mind. All right, so now we get into powers of a matrix. The kth power of a matrix is the product of k copies of that matrix. So A squared would be A times A cubed would be A times A times A, but you can make that A squared times A. All right, so if you already know A squared, then just multiply by A again, you get A cubed, and if you know A cubed, you multiply by A again, you get A to the fourth, and so on. All right, so let's do this. Now they want A squared, A cubed. I'll do this on paper. All right. So we're starting off with this 2 by 2 matrix A. So A equals the matrix, matrix 0, 1 in the first row and 1, 0 in the second row. And they first want A squared. A squared. So again, that's A times A. So I'm just going to do 2 copies of it. So there's A times A. And again, this is a 2 by 2 times a 2 by 2. The result will be a 2 by 2. So I'm going to have 4 entries to fill. First row, first column. Take the first row of the left matrix with the first column of the right matrix. Do the dot product. 0 times 0 plus 1 times 1. You got a 1 times 1 in there. You're going to have a 1. All right. Then first row, second column of the product is, the first row of the left with the second column of the right. Dot product. 0 times 1 plus 1 times 0. There's no 1 times 1 in there. So that's going to have to 0. Then second row, first column, second row of the left with the first column of the right. 1 times 0, 0 times 1, that's 0. And then second row, second column, second row on the left with the second column on the right. 1 times 1 plus 0 times 0. There's a 1 times 1 there. So you got 1. So there's A squared, all right, with rows 1, 0, 0, 1. Then A cubed. Again, you can do A times A times A. Take it 2 at a time like that. Or, I already found A squared. Just take A squared times A. That's A cubed. Now A squared we found was this 1, 0, 0, 1. And A is the 0, 1, 1, 0. Alright, so let's multiply these. Now again, it's a 2 by 2 times a 2 by 2. All our matrices here are going to be 2 by 2s. First row, first column. First row on the left, first column on the right. There's no 1 times 1. Okay, first row, second column, first row on the left with the second column on the right. There's a 1 times 1 in that. So 1 there. Then second row, first column, second row on the left, first column on the right. There's a 1 times 1. And then finally, second row, second column, second row on the left with the second column on the right. There's 0 and 0, 0. So there's A cubed, there's A squared, and that's what they were asking for. Right. So A squared was this thing. A cubed was this thing. Alright, and you're asked to do the same in the challenge activity. And there's 5 levels. I think they might ask for some different stuff each time. But select the row of A and the column of B whose dot product would be the entry A times B, the product of A and B in the 4th row, first column. So this is the 4th row of A. So I put a highlight there on the 4th row of A then I do the dot product with the first column of B. That's all they're asking for. Very, very simple, that one. Now let's look at some other levels. This one is just, what's the dot product of row 3 of A with column 2 of B? All right, so again, it's going to be 0 or 1. We're doing Boolean arithmetic here. And let's see what the 5th level looks like. So this is just fill in the blank for 3 positions. Right? If I was to take A and multiply it by itself, right, well, it's A squared. And just fill in these first row, third column, second row, first column, and third row, second column entries. Okay. So now, why are we doing this? So if you recall in the last section, right, when we were talking about powers of graphs, and how if you had an edge in, G cubed, right, if you look at the graph G cubed, if there was an edge in that graph, that meant that there was a walk of length 3 in the original graph, from one vertex to another. And if you looked at G to the 5th, saw an edge there, that meant that there was a walk of length 5 back in the original graph from one vertex to another. But rather than do what I did in the last section, right, where I did all those compositions and wrote out all sorts of sets of ordered pairs and composed and made the graphs for G squared, G cubed, G to the 4th. now we're just going to take a look at the adjacency matrices and just raise them to higher and higher powers, and we should be able to easily make powers of graphs that way. So if G is a directed graph, right, then the kth power of G, noted by G to the k, represents walks of length k back in the original graph G. So there's an edge from vertex V to vertex W in G to the k if and only if there's a walk of length exactly k from V to W in the original graph G. So matrix multiplication provides a systematic way of computing G to the k. So one, you take the adjacency matrix A for graph G, find the kth power of A by repeated matrix multiplication, and then the matrix A to the k will be the adjacency matrix for the graph G to the k. Very, very simple. And there is a walk of length k in the original graph G from vertex V to W if and only if the entry in row V column W in A to the k is 1. All right, so you can read that theorem there. All right, so for instance, so G here, so suppose G is a graph with 5 vertices, numbered 1 through 5. And suppose A is the adjacency matrix for G. So if you look at A here, A is on the right. They give you the 5th column. So this tells you what vertices map, what vertices have an arrow or an edge to vertex 5. So you see vertex 1, row 1, column 5 is a 1. So that means vertex 1 has an arrow going to vertex 5. 1, 5. Vertex 2 also has an arrow going to vertex 5. Vertex 3 does not. Vertex 4 does not. And 5 has an arrow going to 5. So there's a self loop from 5 to 5 in the graph of G. And then they give us A cubed, which would be the matrix for G cubed. Now when you see ones in here, that means that there's a walk of that length 3, back in the original graph G. So you see here, row 1, column 2 is a 1. That means that there's a walk of length 3 from vertex 1 to vertex 2 back in the original graph, back in G. And there's a walk of length 3 from vertex 1 to vertex 3 back in the original graph G. All right, so and then there's not a walk of length 3 from vertex 1 to vertex 1, or vertex 1 to vertex 4, or 1 to 5. So what is the entry in row 1, column 5 for the adjacency matrix for G to the 4th? All right, now if you want G to the 4th's adjacency matrix, that would be A to the 4th, which would be A cubed times A. So I would be multiplying these two matrices. And if I want the entry in row 1, column 5 of A to the 4th, I'll take row 1 of A to the 3rd and do the dot product with column 5 of A. So what's the dot product of this first row of A cubed with the 5th column of A? There's a 1 times 1 in there, so it would be 1. Then the question after that, is there a walk of length 4 in the original graph from vertex 1 to vertex 5? Well, yeah. You're saying in this first question, there's a 1 in row 1, column 5 in the matrix for G to the 4th. That means that there's a walk of length 4 from vertex 1 to vertex 5 back in the original graph, so yes. A walk of length 3 that starts at vertex 1 could end at which vertices? So this is length 3, so you're looking at A cubed, which I've already looked at up here. And this first row corresponds to starting from vertex 1. So see how there's a walk of length 3 on the original graph from vertex 1 to vertex 2, there's a 1 there, and vertex 1 to vertex 3, and that's it. So just 2 and 3. which vertices have an outgoing edge, right, an edge going out of it that points to vertex 5. And I'm assuming in the original graph, so we're looking at A. And this fifth column corresponds to, all the vertices that are pointing have an arrow going to vertex 5. So you see vertex 1 has an arrow going to vertex 5, vertex 2, and vertex 5 has an arrow going to vertex 5. So 1, 2, and 5. And finally, which walk accurately describes a walk in G of length 4 from vertex 1 to vertex 5? So you see I can do a walk of length 3 from 1 to 2, and then I can go from 2 to 5. All right? I can go from 1 to 2 with a length 3, and then go from 2 to 5. That's valid. That'd be a walk of length 4. If I can go from 1 to 3 in a length of 3, or a walk of length 3, from 1 to 3, but then you can't go from 3 to 5 with a walk of length 1. So you can't do a walk of length 4 from 1 to 3 from 1 to 5 going through vertex 3. You'd have to go from 1 to 2 and then from 2 to 5. So the only one of these that makes any sense at all is this last one, to create your walk of length 4 from 1 to 5. Alright, so again here we're given below. Now you can double check this, multiply these yourself. Here's matrix A, 4 by 4 matrix. Here's A squared. Here's A cubed, which is A squared times A. And again, each of these represents, the adjacency matrix for some graph. G, G squared, and G cubed. So how many edges are in the graph G squared? So remember, I just count the ones. G squared is represented by A squared. And there's 2, 4, 6, there's 7 ones in this matrix. So there would be 7 edges on the graph G squared. Is there a walk of length 3 in the original graph from vertex 1 to vertex 3? Type yes or no. So if I'm talking about walks of length 3, I want to look at A cubed. And is there a 1 in row 1, column 3? Look at A cubed, row 1, column 3, there's a 0. So no, there is no walk of length 3 from vertex 1 to vertex 3 back in the original graph. Starting from vertex 2, so that means go to row 2. How many vertices can be reached by a walk of length 2 in G? So when we're talking walks of length 2, you're talking A squared, right? G squared. So A squared. Now starting from vertex 2, so you go to the second row, how many vertices can be reached with a walk of length 2? Well, you can go from 2 to 1 with a walk of length 2. You can go from 2 to 2 with a walk of length 2, and that's it. There's zeros the rest of the row. So there are 2 vertices. You can go to 1, you can go to 2. There are 2 vertices that you can start at 2 and reach with a walk of length 2. All right, looking at A squared. So again, hopefully watching me go through this, you're seeing how to interpret these matrices, what they're telling you. Okay. All right. Now, we've talked about matrix multiplication. That's the easy one. Sorry, that's the hard one. That's the hard one. The matrix multiplication is the tricky one. Matrix addition is the easy one. To add 2 matrices, to find the matrix sum, A plus B, well, first of all, the matrices have to have the same size. All right, they have to have the same size. Both of them need to be M by N. And if they have the same size, then their sum is simple. It's going to be the same size again, and you just add all the corresponding entries. So you see here, when I take this 3 by 3 matrix A, add this 3 by 3 matrix B, see in the second row first column of A plus the second row first column of B, gives you the second row, first column of A plus B. And it's that simple. First row, first column of A plus the first row, first column of B gives you the first row, first column of A plus B. It's that simple. Okay, no dot products or anything like that. You just add the corresponding elements to get the element of the sum. Now, the addition of matrices will give us the adjacency matrix of the union of a couple graphs. So here you go here. So suppose G and H are two graphs, two directed graphs with the same vertex set. So let A be the adjacency matrix for graph G, and B be the adjacency matrix for graph H. Then the adjacency matrix for G union H, right, where I take the union of all the edges, is A plus B. It's really that simple. And you're doing Boolean arithmetic. All right, so they give you an example here. So here's a graph G. There's 4 vertices, and again, graph H, 4 vertices. So you see these 4 by 4 matrices down here. I got the adjacency matrix for G. Here's the adjacency matrix for H. Add them together, and you get the adjacency matrix for the graph of G union H, right? So that's all the edges of U in union with all the edges of H and put together. And hopefully, you remember how to do union, right? The union is all the edges of this, or all the edges of this, or any edges that are in both belong to the union. And you can see these matching up. Right. So, got an example here. Let's see. I want to eventually. Okay. All right. So what I'm going to do is I'll show you an example where I'll make the graphs corresponding to these adjacency matrices, and we'll look at the sum. Right, so we're given these matrices, and they're supposed to be adjacency matrices for certain graphs. So let's say matrix A here is an adjacency matrix for graph G. All right, and we'll have vertices numbered 1, 2, and 3. Right, this is a 3 by 3 matrix. I'll draw the edges represented by this matrix. We see a 1 has an edge to 1, right? So there's a self loop on 1 here. Then first row, second column has a 1, so from 1 to 2 there's an edge. And the only other one is down here from the third row, second column, so 3 to 2. So there's the graph represented by this adjacency matrix. And then I'll call the graph for the graph with adjacency matrix B, I'll call that H, and draw a similar picture. Again, they have the same set of vertices. Right, it's a 3 by 3 matrix, so I got these vertices 1, 2, and 3. And again, I'll draw the edges in corresponding to the 1s in this matrix. So first row, second column, 1 to 2. Second row, second column, 2 to 2. Self loop. Second row, third column, 2 to 3. Third row, first column, 3 to 1. And third row, second column, 3 to 2. Right? So there's the directed graph, I'm calling H, with that adjacency matrix. Now if you want, I could also even do this, say the edge set the edges of G make a little set, the relation. You got 1 to 1, 1 to 2, 3 to 2. And then the edges of H are 2 to 2, 1 to 2, 2 to 3, 3 to 1, and 3 to 2. Right, you could list the edges if you wished as like ordered pairs, as we've seen. And now what I want is the union. Right? What's the union of these graphs? And it would just be the union of these edge sets. But an easier way to figure that out, what the union looks like, is take the sum of these matrices. So A plus B. Now these both again have the same size. They have to have the same size if you're adding them. And the result will be the same size, right? It's going to be a 3 by 3. So I have 9 entries to fill. And it's a lot easier than multiplication, right? It's just adding the corresponding elements. So 1 plus, I'm adding these now. Right? A plus B. 1 plus 0, 1. 1 plus 1, 1. Remember, it's Boolean, not 2. Right? 1 plus 1 is 1. 0 plus 0 for the first row, third columns, 0. Then the second row, 0 plus 0, 0 plus 1, 0 plus 1, 0 plus 1, third row, right? And 1 plus 1, 0 plus 0. And this should be the adjacency matrix for G union H. I'll draw it. Right, here's the graph G union H. Right, it's a 3 by 3, so I got these 3 vertices. And we're seeing now 1 to 1, 1 to 2, 2 to 2, 2 to 3, 3 to 1, and 3 to 2. And if I wanted to make a set of the edges, again, that's 1 to 1, 1 to 2, 2 to 2, 2 to 3, 3 to 1, and 3 to 2. There's a set of the edges. This is just the union. If you paid attention, or go back and look, this is the union of these sets. Right? The union of these two edge sets makes this edge set, right? You got all these 3 along with the ones over here that don't repeat. And you get this new graph. So doing the sum of these adjacency matrices makes it a lot easier to figure out the union of the edge sets of graphs. Okay. All right. Now, again, you just got to fill in the blanks and all that. All right. Now, finally, Boolean matrix multiplication and addition can be put together to compute the adjacency matrix for we'll call it A plus for G plus. Remember this transitive closure that came up in section 6.5. All right, so hopefully you recall this from 6.5. Remember, the transitive closure of a graph, G plus, was the union of all these graphs. G to the first, union G squared, union G cubed, all the way up to G to the nth, or the nth, sorry, if you have n vertices. And so the matrix, the adjacency matrix for the transitive closure, A plus, is just A plus A squared plus A cubed plus all the way up to whatever A to the nth is. All right, and then when you're looking at the graph, when you're looking at the matrix A plus for the transitive closure, if you see a 1 in row V column U, that means that there's a walk of some length, any length. There's a walk from V to U back in the original graph G. All right, so for example here, I'm pretty sure that's it, yeah. So here the matrix A given below is the adjacency matrix for a directed graph G with 4 vertices. The matrix A plus below is computed by calculating A squared, A cubed, and A to the 4th. And again, you don't have to go higher than the number of vertices. So if there are 4 vertices, it's a 4 by 4. You only need to go up to A to the 4th power. And then add those. Right, this A plus is the sum of A to A to the 4th. A plus A squared plus A cubed plus A to the 4th. So it would take a while. Right, you'd have to calculate A squared, then take A squared times A for A cubed, then take a cubed times a for a to the fourth, and then take those four matrices and add them up, and then you get a plus. All right, so the rows and columns of the matrices are numbered 1 through 4, corresponding to the vertices in G. Okay. Now looking at, all right, so this is the adjacency matrix for graph G, walks of length 1. This is the adjacency matrix for G plus, the transitive closure. And if you see a 1 here, it just means there's some sort of walk. There's a walk of some length from one vertex to the other. All right, so question 1. Is there a walk in G that starts at vertex 4 and ends at vertex 2? So notice it just says, is there a walk, any walk? So I'm looking at a plus, because the 1s and 0s and a plus tell me if there is a walk of any length or no walk of any length from one vertex to another. So starting at vertex 4, so row 4, column 2. Look at row 4, column 2. There's a 0 in the a plus. That means that there is no walk from vertex 4 to vertex 2 back in the original graph of G. All right, let me actually show you. All right, let me go back and graph G on a piece of paper. All right, so hold on just a second. Okay, so there was the adjacency matrix A that they gave us. And you got 4 vertices. It's a 4 by 4 matrix, and let's call them 1, 2, 3, and 4. Just going around here. Now this is graph G. All right, G of the first, A of the first. And I'll draw, you got 1 to 2, 1 to 3. All right, then 2 to 1. That's it. And then 3 to 4. And then 4 to 3. Now the question was, is there a walk in G that starts at vertex 4 and ends at vertex 2? So let's see, I can go 4 to 3, and then you can't get to 2. You can only go back to 4. So there, like I said, there is no walk that starts at 4 and ends at 2, which you saw from the A plus matrix. Row 4, column 2 had a 0. So there's no walk of any length from vertex 4 to vertex 2. Is there a walk in G? Any walk? So again, we're looking at A plus, the transitive closure matrix. Is there any walk in G that starts at vertex 2 and ends at vertex 4? So that's row 2, column 4. Yes. See, row 2, column 4, there's a 1 in the A plus. That means there's some walk from vertex 2 to vertex 4. Now let's look at my picture. Let's see if we can figure one out. So starting at vertex 2, can I walk around this graph and get to vertex 4? Yeah, I can go 2 to 1, 1 to 3, 3 to 4. Yes, there's a walk of length 3 from vertex 2 to vertex 4. Now there's no walk of length 1. See, row 2, column 4 of A is 0. I can't go directly to 4, but I can get there, and that's what A plus is telling me. Right? A plus is telling me I can get from vertex 2 to vertex 4 somehow, back in the original graph. So yes. And then last question here, how many vertices can be reached by any walk in G? So again, I'm looking at A plus, any walk. How many vertices can be reached by a walk in G starting at vertex 4? So I go to row 4 in A plus. I can't reach vertex 1. I can't reach vertex 2 by any walk, but I can reach vertex 3 and vertex 4. So 2 of them. And back on my paper, right, here's graph G again. If I start at vertex 4, right, I can only get to vertex 3 with a walk of length 1, and I can get to vertex 4 with a walk of length 2, and that's it. I can't get to 1, I can't get to 2 if I start at 4. So there's only 2, and again, you can tell that from the 4th row of A+. There are only 2 vertices that I can reach when I start at vertex 4. All right, and then again, this last, like in the end of section 6.5, there is a proof here that's a proof by mathematical induction. See this proof by induction. And as I mentioned last section, you can read through this proof if you want. And if it makes sense to you, fantastic. If it doesn't, don't worry so much about it. I'm not going to test you on it yet, because we're going to get into talking about how to prove things, how to do proofs by mathematical induction in, I believe, Chapter 8 or Chapter 9. It's coming up. So again, you can read through this if you wish. If not, I also understand that. And yeah. All right, then you have your additional exercises. Some of these are on assignment 7, some are not. I really think I have the first 4 of these. I just think just 665. And you know what? You could do all of these without worrying about mathematical induction. All right, so that proof by induction there has no effect on any of these exercises. So I would recommend trying all of them, even though some of them are not assigned on assignment 7. Get some more practice, get some extra exposure to the material. You can of course look at the solutions as well. Check to see how you're doing. And yeah, that's it for section 6.6 here. Going over matrix multiplication again, Boolean matrices, and matrix addition, Boolean as well. Only ones and zeros should be showing up. And how they're related to graphs. Right? When you multiply a matrix by itself, do a squared, a cubed, you're getting the matrix, the adjacency matrix for the graph G squared, G cubed, and so on. And when you add matrices, you're getting an adjacency matrix for the union of two graphs. All right. So of course, if you have any questions, please let me know. Unless it's on induction. All right, if you're reading through this induction proof and you're not getting it, don't worry about it. All right. Save your questions on mathematical induction until we actually cover it, which will be, like I said, I think in Chapter 8. But other than that, if you have any questions on matrix multiplication, matrix addition, transitive closure, graph powers, any of that stuff, let me know. And thank you very much for watching.